What is the theory of everything? What does the theory of everything seek to accomplish?
I get a lot of emails. I'm sure both of you guys do. I've got this theory of the early universe. I need to, or of grand unification. Can you help me prove it? And I'll share, my Nobel Prize proceeds with you. I actually asked that of Adam Rees, and he said, yeah, how do you think I won the Nobel Prize in physics?
I did get somebody who sent an email from actually somebody I had never met before, and said, hey, do you know what this conversation online? And somebody had noticed an equation that could close to predict the fine structure constant.
The fine structure constant. It's a dimensionless description of the strength of the electromagnetic force.
What about experimental validation? Is that a fair standard to hold before a theory of everything that's trying to unify quantum mechanics and gravity?
Remind you, this is our Mars rover moment. 10 years, thousands of years of effort, suddenly in one moment being revealed to the collaboration. And lucky for you guys, you get to see that moment as we recorded it.
The number we had predicted is right here. Safely right in the experimental average. Right? Beautiful, beautiful. And more important, notice I give a little thickness to the line there just so you can see where it is, but it's a line with no thickness. That's an exact geometric prediction out to any digit you want. Okay, beautiful.
What you see here is the frequency on the clock on the lower number.
39997844.
7844.
Same number. Yay!
Yep. It's the same number.
And this is what we get.
Whoa!
Wow!
Wow. Oh my God.
We confirm page 21.
These are the central parameters that encode our geometric understanding of reality. Literally, to the error bars. This literally lists the most important constructive parameters of existence.
To see a world in a grain of sand, and heaven in a wild flower, hold infinity in the palm of your hand, and eternity in an hour.
Well, that's a pretty bold claim, sir. Hey guys, what's going on? Reeves here. And I'm joined for the second time now by Mr. Thad Roberts to discuss his new work, 44 Derangements and the Shape of Persistence. So, Thad, what's going on? What's the good word, man?
Well, everything's going fantastic. It's hard not to be excited with an introduction like that, right? The most exciting topic humanity's been able to weave together so far, or the end fringes of that topic. Where we're at, yeah.
Well, why is a pretty big question, and
there's
a lot of answers here. There's a lot of answers that a lot of folks have been searching for, discovering, and it's just one of those stories where we literally now have a story of why. Okay, we have all these numbers, we spent all this money, we've dedicated all this person power over these hundreds and thousands of years of humanity discovering where we are, what's actually going on. Now, for folks that haven't come across any of your work before, there's things in the doobly-doo, links to Thad's book on Amazon, as well as his YouTube channel as well. Thad, why don't you kind of let us know how you came across and went about this quest?
Wrote work. Hours and hours and hours and hours of asking questions. So the biggest trouble in life usually is trying to figure out which questions to be following, which things to be paying attention to, right? The nice thing in the field of physics is the field itself is oriented at trying to ask the right questions and trying to find out what is the structure of reality? What's it fundamentally composed of? What are the rules for interactions? What just fundamentally is it? And we have a prescriptive answer so far. We have a geometric answer of how certain boundaries geometrically, symmetrically exchange, right? Called quantum field theory or Dirac's equation. But we also have all the parameters of that symmetry exchange. They're not part of Dirac's theory. They're not part of the equation. They don't come from it. The symmetry is perfectly balanced in the equation, but all of the actual parameters in this exchange, meaning all the actual unique ways that this balance breaks up, have independent parameters to them, scaling, stretching parameters that we know from experiment only, right? So the speed of light, or Planck's constant, the gravitational constant, the electric constant, the magnetic constant, or the whole 44 list of all the unique parameters we have in physics, they're the current puzzle pieces of reality, right? So they're the things we've fought for. We've gotten measurements to different amounts of significant digits, some of them all the way out to almost 14 significant digits, which is a lot of precision, okay? These are the things that are, you might say as a treasure hunter, the most valuable conscious treasures there are so far on our planet, right? Those are the data points that are the hardest to earn and that tell us the most about reality we have so far. But in physics, there's no current story at all connecting them, explaining them, predicting them. Any of those three. There's no story on any level of where these parameters come from. So that's what I wanted to search for. That's what I wanted to look for. Now, of course, when you're searching for a story, in order for it to count, it needs to explain the parameters that you're trying to explain, right? So we know what kind of thing counts as a story when we're at the end. It needs to explain the parameters at the end point. But also, we know we're looking for an elegant story. So you might come up with 100 different kinds of stories. Ideally, it's nice if you have many to pick from. So far, we have 0, right? But if you're looking for all the possible ones, you're also interested in the most elegant among them, because you have a suspicion that elegance comes with its combinatorial explosiveness. It comes with this ability to kind of go into anything, but it also gives you a more powerful kind of explanation than something that doesn't. So we're specifically looking for the richest kind of explanation. We're going here because we're looking for the most elegant one, meaning ultimately we want to have an explanation that you can hold intuitively in your head, a framework, a perspective, a way of conceiving the inputs from reality that you're getting, that gives you more visceral access, but a deep level of understanding, a way to predict the actual parameters we're measuring. Not just measuring them and get them, but a way to predict those partition parameters, all those constants. All right, so after looking for years and years and years, the majority of those days being over 12 hours a day, playing on Wolfram Alpha, asking questions from the data points. What do I mean by that? I mean, when you look at the set of parameters that we call the constants in nature, we have, 44 constants in nature. We have 17 specific parameters of mass, so unique mass assignments for the fundamental particles, right? And we also have charge. We have the electron charge as a unique value for charge, and we have +1/3 and +2/3 of that charge and 0. So those are all the unique specific parameters we need in quantum field theory for it to actually do what it is supposed to do. All right, that means that list, well, as a set of parameters, what does it represent? We usually just get a number, right? You're going to get a number, usually 1 digit, and then so many digits after the decimal point, times 10 to the some power. So we always put them in this scientific notation. So they can be completely different scalings. The power tells you the scaling of them, but they can also be completely different string of digits. And that's all we get reported to us, except for we also get the dimensions. Okay, so we have a string of digits, we have a power, it gives you the scaling, and then we also have the dimensions. So somehow this information is telling you a relationship between these dimensions. And that's all we know to begin with. So not knowing what the story is supposed to be, I decided just to search and ask every possible question, meaning asking every relationship between every one of those constants in nature I could invent in my head. This one divided by that one, this one squared divided by that one, times by this one, and so on, over and over and over, not claiming I got them all. Obviously, you can't, there's an infinite number, but everything I could come up with, I asked. And then, of course, because Wolfram Alpha is privy to basically every constructible number, every geometric number that we can define, it knows, right? When you ask those questions, it can spit out a number you don't know that the answer you're getting is necessarily right. You might not even know what it means, right? It might spit out a parameter that you've never heard of before, but it leaves you down it gives you another way to fall down. Instead of a wiki hole, you get to fall down the Wolfram hole, right? You get to,
I've spent a couple of nights doing that more recently, which is one of the reasons I want to have Jen on in a little bit. Just going through and just, it's like what you just described right there. I feel so much better about myself just because I'm sitting there. I'm like, what happens if I do this? What happens if I do this? It's like, do I happen to recognize this? And every once in a while, you're like, that's very interesting. And you start to gain an intuition for what's actually going on. I'm sorry, sir, I cut you off.
That's dead on. That's the process. And the trick of the process is to figure out how just to keep going with the process. You're always ignorant. That's why we're in the process. You're always unaware of something. So that's not the thing to be afraid of. But to stop asking is the thing to be afraid of, right? All right. So eventually, it took a long, long time. And then there was a 10-year gap, honestly. So I'll speed that story up. There's a 10-year wall where I couldn't come up with anything new. I was re-asking the same questions over and over, hoping I just missed something. But it was just doldrums. There was no wind in the sails. And then somebody sent me somebody who was a fan from, I think, Einstein's Intuition, who I'd never really talked to before, sent me an email, pointing me to a discussion online in which somebody had noticed a really simple hyperbolic way to get close to the fine structure constant. And of course, then I just asked, well, how far off is it? Meaning, how much do you have to modify this thing to get it to exactly the fine structure constant? It turns out you just had to minus the Planck mass boundary from it, right? That was the only adjustment. I rewrote the algebra of it, but other than that, you just had to minus the Planck mass boundary. And that got me really excited. I mean, right away, it wasn't clear exactly what this meant. I mean, algebra and math wasn't my strong point in life. My focus had been on the physics, trying to interpret the story of what's going on, trying to imagine new possible geometries fitting together to explain quantum mechanics and so on. But seeing that way was kind of new. So at first, it just seemed like a miracle, but a miracle I couldn't ignore, right? First, I also knew that you couldn't so easily do that. You couldn't just get close to the fine structure constant. How? Because lots of people have wanted to for a very long time, publishing PhDs, all kinds of papers, trying to come up with ways to get close. And they come up with very artificial looking ways that don't get you so close, right? So it was, for that reason alone, something I could ignore. It's at least closer than anything else. And it got all the way from just one simple modification. Well, it took a while to look close enough. It always does, because when something's new and it feels a bit like a miracle, when you don't investigate as much as if you know it's the biggest clue ever, right? At some point, I switched from feeling like a miracle to knowing I'm on the biggest clue ever here. This is what I really have to look at. Actually, let's split here. This, can we see here? Yeah. This is the part, this is the equation I'm talking about. This is the hyperbolic vortex equation. And we just had to put the Planck mass boundary here as the modification, okay? So this equation here, it's really just looks like the unit equation for hyperbola. It's the hyperbolic connection, except for it's self-closed, wrapped around a circle. So it's the only modification. Well, the solutions allowed for this geometric arrangement, bounded by the Planck mass boundary, has these 4 answers. There's one thing that slowed me for a little bit is I only translated in these terms. Let me turn to this picture here. These are the 4 solutions, but you can also talk about 3 and 4. So J3 and J4 can also be turned in Jr, the radius, and the angle. So you can talk about them in X and Y projections or radius and angle projections. And I hadn't checked the radius and angle ones for a while. So this is one of the big updates in the concepts of nature coming up in the new story. But anyway, the solutions here, these partition solutions, don't just relate to the fine structure constant. How? The first solution squared is the fine structure constant. Right. Perfectly, okay? That's really beautiful, but also we have these 3 sisters that go along with it. They're geometrically, fundamentally always there if it's there, okay? Why are those other ones also interesting? Well, if you take all 4 of them, multiply them together, so take their product, you get 2 pi, which even a beginning geometer knows is just a circle, right? That's extremely interesting geometrically. If you add them together instead, so instead of taking their product, you take their sum, you get 0. Also, one of the most interesting things you can get either algebraically or geometrically. If you take just the real parts in atom, you get 0. If you take just their imaginary parts, you get 0. If you square them first and then add them up, you get what we call the quadrants. The quadrants is a sphere. Technically, quadrants is both the sum of the squares and the difference of the squares. So you get, in this case, the sum of the squares, a negative 4 pi. If you take the difference of squares, you take a positive 4 pi. So as you can see, this thing is, in terms of a partition geometry, one of the most beautiful things you could ever have. Its partition centers combine in both product and sum formation under the most simple possible cyclic balanced forms you can have.
I noticed. It's a very beautiful thing.
Yes.
See, here's the thing. Not only because I remember, and still in part of me, I'm like the gentleman on one of the videos. Is this a math trick? Because if this is a math trick, this is the most well-staged math trick ever, because I'm like, I type in the numbers, I type in the variables, I look at the notation, I look at the data, and it lines up. And just a kind of a real quick recap of just what ended up happening. I'm like, okay, let me, oh, look. Oh, here's a physicist gentleman that I happen to follow from Professor Keating. Oh, I was looking for some drama content so I could push back on whatever people were getting a little bit out of balance on. I'm like, oh, okay, source code 7. Let me click this. Get in 14 minutes or so in. And I'm listening. I'm like, okay, it's geometry and everything. It's listening. I'm like, if half of this stuff is right, this is the most revolutionary thing I've ever heard of. The very next day, the muon G2 results were released. I listened to them at work. I'll send you a quick tweet. I'm like, does this help your model? Yes. I come home. I check what the muon G2 results were. I checked the video that I was listening to while I was out on a run, and confirmed. At that point, I'm like, okay, let me take what you had said. What if I assumed it was right? What would need to happen?
Mhm.
And at this point, I'm like, okay, now, again, a lot of folks, they end up, it's kind of like within media, I feel like there's almost like a social gravity. I think they call it gravitas as well. And a lot of folks are saying it's like, all right, these are the people that people are talking about, so we need to listen to what they're talking about. I'm like, okay. Now, how many times over the course of history might somebody have had a revolutionary idea, something that could help us jump ahead, but maybe they didn't have the ability to communicate it. Maybe they didn't know how to write. Maybe they unfortunately perished far too soon. It's just now that we have the internet, we have the ability to put this out there. We have the ability to actually publish books en masse, to get information out there. The problem is we've also made the word often cheap in a way, because if everybody can do it, and hey, power to the people. My thing is, it can be difficult to sift through, and it's like, well, somebody did this flare, somebody did this. And again, the muon G2 thing, I'm like, people are making a big deal about this. How the heck could I randomly click on a video that brought me to one of the most revolutionary things ever? Those results are released. I go on the internet, I use Wolfram Alpha, I put these numbers in, the numbers come out. And this is why I started making the little series of how I stumbled upon the best theory of everything yet. Because that's kind of an overused term, and one of the reasons why I kind of believe you're a serious person is because you don't go around labeling everything theory of everything. Than the sheer fact that the book's name is 44, which kind of corresponds to the 44 constants of nature, along with the number of actions that happen to go into the central balance, if you would, of the Planck time itself.
Mhm.
And if you just want to sell a bunch of books, you actually just add up the total number of derangements, get 137, and then people will be like, oh, look, the number. And the fact that you didn't do that and you don't use as many capital letters is what makes me think you are a serious man.
And you don't use as many capital letters, you said.
No, because I'm the opposite. I'm very hyperbolic in that manner. And
my aim, honestly, is to have it make as much sense to me as possible. So I'm trying to whittle the story to the most clear, precise geometric picture possible, right? So that's basically what I'm after. Let's do a quick review of the whole story, because we might have a little bit of better language to work with now. Before that, we had a little bit of slip up with what we were calling the universe, or what's the whole stage called, and so on. Now I'm going to go with this construction that we're talking about. We're going to call it the minimal stage, okay, or the minimal arena. Okay, and by that I mean we're going to start out imagining there's an infinite void, but there's nothing in that void that persists. So nothing of interest in the sense that we can go measure it. It doesn't have a property that is around more than once, right? So there's nothing interest. And then the minimal possible thing of persistence, meaning the minimal stage that continues being itself, occurs. Okay. Now, whether you think it's a big miraculous event or an easy event to occur, that's not where I want to go with the topic. What I want to go where is, what does that stage look like? The minimal possible one. And what do we mean by minimal possible? How could there be a minimal possible stage? Well, I mean, it's a partitioning, it's a wave of action that finds a way to separate such that it makes no gaps, so it remains a manifold. But that separation partitions an outside from an inside consistently. It always maintains a break between them, so that everything on the inside stays on the inside and everything on the outside stays on the outside. There's other things happening, but that's always true. Okay? Well, there's a minimum possible in geometry, available to geometry, the minimum possible 3-manifold. And there's a minimal possible volume complement that's a double cover of that minimum 3-manifold, called the hyperbolic figure-8 knot. So this minimal stage internally, if it's going to be understood geometrically, would have that shape. It would be wrapped by the boundary of the hyperbolic figure-8 knot. Now, the outside portion of this minimal stage will have an internal boundary that's very related. It's made of the same parts, but they've been rotated and oriented and under a different arrangement. Okay, same parts, but put under different arrangement because they're external now. Well, that external projection eventually goes out to a sphere, what we call the great sphere. But the inside of the sphere, as you go towards the internal boundaries, you can't go all the way to 0. There's a cutoff, okay? So in this external domain, you have to be so big or bigger, right? There's a scale range in that domain. But as you approach the smallest cutoffs, which are the Planck mass and Planck charge boundaries, there's two different size cutoffs. As you approach that, then the way that this sphere is divided up is 4-dimensional. Okay, the wave action is being partitioned in 4 or two different circled planes. All right, so that single stage, that minimal possible stage, which is defined by the minimal volume complement on the inside and externally defined by the counterbalanced N hypersphere of maximal volume. So we have a geometric form whose inside is the minimal geometry and whose outside is the maximal geometry in terms of N hyperspheres, okay? That whole construction is what we're talking about as the minimal stage now. Just one of those, a single one, is a minimal stage. Now it can be more complicated because you could intersect several of these stages. I'm not gonna go anywhere there in the conversation. We're gonna just stick with the one minimal stage. What are the attributes of the stage? Well, the inside's the easiest part to nail down because it's just two different actions trapped together inside the hyperbolic figure-8 knot motion. But the outside's got more parts, and, well, the inside and outside had the same number of parts. They mirrored, right? So you can talk about, there's easier ways to pin down properties from the hyperbolic figure-8 knot and easier ways to pin down properties from the N hypersphere of maximal volume and so on. And you can use those to zero in on the properties. But the biggest point is, when we talk about this minimal stage, it has 5 total rotations in it. 2 rotations inside that define the structure of the hyperbolic figure 8 knot, and 3 rotations outside. These are all unique numbers, unique magnitudes of rotations, and they're all assigned to completely different scaled actions in this minimal stage. The smallest of those rotations is applied to all of the derangements, all 44. In fact, it's the highest resolution of the picture, so in a way it tells the whole story of the picture. So all derangements, which would be this equation right here, so all of our derangements is worth 44 of them, is equal to d naught. So all of them are equal just our hyperbolic minimal circular division, and it has to be counterbalanced because there's 5 parts in the total structure. So we just make a minimal circle, and that equation characterizes, when you apply it to a double cover of 44 derangements, it characterizes the Planck boundary itself. So that means the Planck time boundary. So that means the Planck time characterizes the smallest possible partition action in this complete 5-part minimal stage, the 2 of which on the inside define the Planck time and then the Planck length. So Planck time and Planck length combine to define the shape you're showing right here, that boundary. Now, of course, that's how, if it's a first time view for anybody, the boundary doesn't have, the one we're referring to doesn't actually have the cutouts that you see. The cutouts are so that we can see inside. So imagine this shape, but fill in the cutouts in your mind, and that's the boundary we're talking about. And then you can see what we mean by it's dividing an inside and outside. If you fill in the cutouts, you could color the volume on the inside with dye, and it wouldn't leak to the volume on the outside. It's just separated. Okay.
Yeah, it's kind of like the peel on like an orange or something.
Yep. Yep. All right. So the minimal possible geometric way to separate this arena, right, means that we also have exponential separation. So to make the story faster, we have 5 separate boundaries under 5 balances that have external rotations and internal ways they partition. And it's all hyperbolic. And those 5 rotations define all 5 of the Planck constants in one minimal arena. So we have the minimal possible geometric arena whose minimal internal volume complement defines the hyperbolic figure 8 knot, and whose external volume complement is the n hypersphere of maximal volume. And its 5 rotations in its partition balance define all 5 boundaries we call the Planck constants, the boundary of time, length, charge, mass, and temperature. So that's a fantastic start. We have a stage under 5-part rotation, which means it's being split up, striped into different scaled actions, and then zipped perfectly back together, right? We're understanding a manifold in a much more richer way, excuse me.
Yeah. It's one of those things where I start taking a look at this, and what just comes to mind is, and again, I don't have like all the history, and maybe that's a good thing because I don't have so many priors, because I remember I learned how to ride a motorcycle the wrong way, and then I took a class and I nearly failed the class because I had learned the wrong way. But it was just one of those things where I take a look, and when I see this, I'm like, okay, well, this is generated by the hyperbolic figure 8 knot. I'm like, okay, that's going around and around like this. Like if you just had that action just within, let's say, like a fluid, and if everything had some basically either minimal or maximal viscosity, I forget which direction it needs to go, but wouldn't it generate something that kind of looks like this?
Yeah, that's the question here. So this is the claim that would be the minimal thing you could generate. If you want the system you're generating to include its own boundaries, right? You're not maintaining it yourself, or you're not including some other exterior stage that's responsible for it. The minimal thing you can have that includes its own boundaries would be, well, that would be half of it. That would be the inside part. Yeah.
I'm sorry, I completely cut you off that.
Right. Well, so the next step here is that we now have not just a matchup with all the Planck constant definitions. So all the black digits here are the ones that we have as known measurements for the Planck time, length, charge, mass, and temperature. And then the green ones now are from this geometry. We can then extend to all of its digits. We now have a prediction for those boundaries as far as we want. Now, what does that mean as far as we want? Well, we want out to 14 significant digits because our basic measurements and all of our constants in nature goes all the way out almost to there. So we're going to now use all 14 significant digits of all of these. And now we know these boundaries precisely, which means what? Which means if our constants of nature are composed of these boundaries, we can now ask questions to several more significant digits, or as far as we want, that we couldn't do before, right? Before you were asking questions like, let's take the Planck length divided by the Planck time, or the Planck charge squared divided by the Planck mass. You, using the data, would only have an answer to so many significant digits. Now we have a prediction to all significant digits for these, so we can ask far more questions. And why that gets even more exciting, when we apply that to asking questions about the constants of nature, so just these two rows right here, be all the constants of nature, we find that with the 5 Planck boundaries, and with the understanding that, let me bring this up here real quick for a second, with the understanding that this partition structure externally balances on 2 different domains. It has the throat and it has the back end of the vortex. So you have 2 different expressions always being balanced. You have the terminal end here, and this terminal is always the arrangement of the Planck length times the Planck mass divided by the Planck charge squared. I see I just have a typo there. To fix that one.
I remember there being a quote from, I believe it was an individual I hadn't really heard of before. And when I was going through, I'm like, that's very interesting. I'm like, that person basically said what you just said right there. It's like, it's going to be based upon the charge boundary or something. It's going to end up being a 2 or something. This is why I have the book.
So under this structure, just under that one arrangement, that our external projection is under hyperbolic vortex arrangement. So it's bounded both by a throat of the vortex and by the backside. Okay, so it has 2 different scaled bounds. But using that mathematical or algebraic construction, okay, which means it's a partitioned balance. We're understanding there's 2 sizes of actions that are in play, but they have to both be geometrically balanced. That means that we can use that prescription, which is a pretty simple equation, to go look for what the balances of every constant in nature is. Meaning you have that one prescription, you can now go look up on Wikipedia any of the most useful data points in all of physics, right? So pick up anything that's in one of the parameters of quantum field theory, so the electron charge or the electron's mass or any of the other parameters. Make sure they're listed in one of the fundamental dimensions. So it needs to be in seconds, meters, coulomb,
scientific units. It's a pretty good system, I hear.
SI system. And then translate that data point with its dimensions in terms of this one equation, right? I mean, you can just pull apart its pieces and then find out what its terminal geometric action is. Find out what its primary geometric action is. You don't even need me at this point, just knowing that equation. So that prescription alone gives us a way to investigate algebraically, without any other training. You can all by yourself now investigate using an algebraic tool that we didn't have before.
See, that was the thing, and thank you so much, just because that helped me, because there was something that I noticed, because I was plugging these things in, and I kept noticing, like, I'm like, all right, I'm almost at the mass of the electron. It's good for, but that last digit or so is just like, what's going on? And I realized, I'm like, wait a second, I'm pulling out these other things that basically were either a measurement or kind of like a rough thing, and like right every time I would get around like 7 or 8 digits or so in, I'm like, it seems to be just a little off. And I'm like, all right, I got to call Thad on this. I'm like, all right, sir, you seem to be off. You made these claims. And then what you just described there, I'm like, intuitively, I'm like, as long as I have the exact, do I have the exact? I'm like, I did not spend the time because I got distracted by other things. But I'm like, okay, there's got to be something in there. I hear the fine structure constant may be changing. Maybe that could account for it. And then I re-listened to one of your more recent lectures you were giving, and you brought up this very important point. I'm like, okay, because I remember you said 14 digits, but I'm like, I'm only getting to about 7. Oh, this is explained away. My other question, if we're going to throw around the term theory of everything, it's like, well, we got to unite quantum mechanics with general relativity, and apparently this is where the units come in.
We're not just uniting quantum mechanics and general relativity. we're doing that in a way we weren't necessarily aiming to do, but we're doing something a little bit larger. We're uniting the tradition of geometry and algebra in another rich way, in the way that we've been seeing over the tradition that it's been going. But we're doing something really powerful here. We're seeing that the simplest language might be the language of derangements, right? We might want to invent this language of partitions or balanced derangements and see things from this way, because using that, all we need is 5 boundaries, okay? 5 geometric boundaries that we can define very explicitly. And 4 connecting numbers. We need pi, which we can also get from those 4 constants, right? We need the universal parabolic constant, which is in a way like the inverse of pi in hyperbolic connected geometry. And we need the golden ratio, and we need Euler-Mascheroni constant. And I know you've heard of the golden ratio before, but it's fundamentally connected to all hyperbolic geometries, including the gamma function. Anyway. I want to hear at this point what the picture in your head is, because we got a simple, basic, minimal construction, and all the unique balances or derangements in that construction define all the constants of nature, and all the unique minimal boundaries of the construction itself define the Planck constants. What's next?
As far as derivation of what we actually do.
What's the next question in your head?
Oh, how does this all flow? How are these connected? How are the hypothetical or hyperbolic gears, if you would, turning? Good,
perfect. So you want to be able to now see the picture where you can see all the pieces that are partitioning and how they're all rotating into each other symmetrically, right? That's exactly. So our next step is we're going to be coding this and building that actually system. I think I got like 70% accurate picture in my head. There's a lot of moving parts, and so I'm going to say I'm 30% wrong. No. From a computer.
Well, this is the thing, and I've been creeping around this internet stuff and things, if you would, exploring, kind of riding the internet's algorithm that I've seeded with a number of your talks, a number of Wolfram physics project lectures as well. And I come across some very interesting things, especially regarding the visualizations. And I've spoken with folks, and some folks were using proprietary software that they could, and that's fine. But I just started asking some questions and showing them some different videos and other information. Asked, is it possible? I got a yes. So I'm hoping good things are coming. And speaking of good things coming, my actual co-host from the Eigen Rangers, Miss Jennifer Scharf, is actually joining us right now. Hi, Jen.
Yeah. Hey, Jen.
Hey. Can you guys hear me okay?
Yeah. Good to see you again.
Yeah.
You too. Hi, Thad. And Memes. Great to see both of you.
So you had some questions. Okay, based upon where we're at.
I don't expect him to have answers for like any of these, by the way. So can I just preface this? Like, it's honestly, I'm just putting it out there, and my expectation is that we're gonna maybe start to be able to think about answering these questions in about 50 years. So I just
that's
some good ones.
All right, I've basically got a mess of notes here. Here we go. Have you given any thought to what the form of the or name of the unified field model when it happens is going to be?
When it happens? What do you mean?
Well, once it's like, do you think it's in a form right now where you can call it a unified field model, or like at what stage of development would you say that it's at right now?
Yeah, I would say it's already. Oh, good, I can see you now. I would say it already counts as a unified field model because it has all the symmetries built in, and more specifically, it's more sharp than a unified field model. So it goes in that step beyond. So what we count as a unified field model right now are more bounded rules of symmetries, right? How all the operations are supposed to work in general terms, but none of those rules specified the actual parameters of the system. None of those rules told us these things. So our construction, its boundary conditions give its parameters also. So it's a field theory, but it's a little more than I think what a field theory was aiming for prior to this.
Metaphysical framing.
Sure.
In a way. because it tells you information that's pre-physical.
Yeah.
Would that be accurate?
Sure.
Like I remember your image where there's the circle and then the 6 circles around it, and you're using that to argue for some sort of a dimensional jump, or that's where you kind of lose me, because I
can scale there's if you start with something that's built from circles, so it's planar and built from circles, and those are our only Lego blocks, so you can only make something from circles, then the next biggest circle construction you can make from just those circles would be composed of a total of 7 circles. That's all. It's just a circular geometry thing. It's not that profound, but it's something to remember as a geometric rule.
That was another thing that I noticed, because as soon as you were doing Scharf Cohost, Kevin, and I saw those 7 circles, I'm like, I had met Jennifer a few months before this, and she kept grinding into my skull. Pay attention to this. I'm like, I've seen that diagram before.
Why? Jennifer, what's your interest in that?
This is why I wanted Jennifer to come.
I feel so bad. I feel so bad because I'm like trying to teach him, and everyone in the chat's like, why are you being so mean to him? I'm like, because I'm like, first of all, I don't think I am. I'm just really passionate. But anyway, if I was too harsh, just because it feels like he's right, like he's this close to getting it, then I just got to give him that extra little push. But I think the reason why that diagram, or just as I give it a couple more thoughts now, is that the metaphysical primitive is a boundary. So everything is built up from boundary, and then you can do a bunch of things to these boundaries. And at some point, you realize that this 3+1 dimensional form is the boundary of boundaries, maybe the ground of boundaries,
or the rules, or the geometry. Well, okay.
I honestly, this is why I don't expect the answers to these questions right now, because it's still up in the air, and we just have to. Like it's just, this is what just came to me, with statistically distributed minimal deviations from a small set of information-rich geometric primitives. One of those would be your shape, but the religion has a bunch already that have already been established. So I sent that image to memes. I sent a bunch of images.
Now, before we get into the metaphysical, this is what also gives me confidence.
You could imagine something that looks a bit like a soup can. So you've got like a sort of you've got a cylinder. So you've got a bulk gravity theory on the interior of the soup can, and you've got a sort of quantum field theory on the boundary of the soup can. And somehow, just by knowing the quantum field theory on the boundary, you can determine everything about the gravity theory on the interior. And so it's in cases like this where, as you correctly allude to, the notion of whether the universe is really 3-dimensional or really 2-dimensional becomes a little bit subtle, because you could say, well, the sort of gravitational part of the universe, the bulk part, is 3-dimensional. But the quantum field theoretic bit that encodes that bulk theory could itself be 2-dimensional. Everything going on in the 3-dimensional universe could be encoded on a 2-dimensional surface at the cosmic horizon.
If we have a proper label on the can, will we be able to tell the soup on the inside?
Yes, right, exactly. That's precisely the point, right? That everything there is to know about the soup, you can infer just by knowing the label on the exterior. Yeah.
Cool. It's this is and again, I'm sorry, that was kind of a metaphysical thing there, but just as far as parameterizing what's going on, I'm feeling good.
Cool. All right, Jen, over here, some more of your questions.
Oh, thanks. I appreciate that. Not exactly sure where to start, because I've got like this huge. Okay, would you say the universe is fundamentally physical, material, mental, numerical, geometric, pinball machine from hell, or something else?
Yeah. It seems to have a lot of things in common with being a code. So I have a lot of questions around that direction, and I entertain a lot of the options as long as they're seriously proposed. I think it's really interesting to point out that you could ask, is it algebraic? Is it geometric? And in a way, you can't tease those two questions apart. They mean something slightly different, but they also mean the same thing. It's just, I don't know.
How is a picture different from a book? A book is a bunch of words in a series, and a picture is one single thing. So we'd say that the picture has a quality of non-duality that the words don't. So the geometry has a non-duality that the algebra doesn't. And maybe I can just share this real quick. Because I realize like I try to go through the logic of this with people. Am I still coming through okay?
Yeah.
Mhm.
I try to go through the logic of this and I just lose people, you know. It's a Socratic shuffle, or it's a, well, I don't agree with this premise and I want to argue for 45 minutes. And Memes has seen this, I'm sure, many times that I get into it with people. And the original point is just like, we can never actually derive the thing that we were trying to, like the point that I was trying to make in the answering the first question is just a wash and a morass of nonsense. So I realize
got
that not
some
everyone
fungus
is
among us.
understanding. They're not understanding what I'm saying. So I made this diagram here to illustrate a little bit better.
Yeah.
And this is geometry that may not have an algebraic form in our current representation of algebra, but theoretically we could just change algebra so that it was on par with geometry and the same level of non-duality. What do you think about that?
I didn't think you were done with the sentence.
I didn't want to keep rambling, and if people weren't following, because when I get into dualism and non-dualism, I realize like, okay, no one is necessarily going to know what the heck I'm talking about, but
I think there's self-reinforcement.
I think I'm finding a lot of dualism between algebraic geometry or geometric algebra. Right. So I like to look for conditions in which I don't see the dualism, which means that there's a thing I can only view from
I think
one
you mean
side.
mapping. When you say dualism, you mean mapping, right?
Partially, yeah.
That's not what dualism is. Dualism is the existence of polarity. So an image has a lack of polarity because it's just one thing. A single image is like, if I have a sphere, it's a sphere. I cannot make it any simpler. Whereas an equation is necessary. Okay, a sphere is non-relational. A sphere is non-relational, an equation is relational, and that's really important because the fact that they're not the same thing makes it so that it's really hard to reconcile something we intuitively feel we ought to be able to reconcile.
Wait, did you say a sphere is non-relational?
It's relational in a sense, but it's everything we're talking about is relational right now. It's about a degree of relational. So an equation is more relational, aka dual, than a sphere because a sphere has its own intrinsic existence. And an equation is always relational, as in the left side equals the right side. There's always a cut in it, whereas a sphere doesn't necessitate a cut.
Maybe a partition.
But a sphere is a partition, so a sphere is dualism. But an equation requires a bunch of other dualism, right? Because you have to define the dualism of whatever your numbers are that are represented by the equation, right?
Requires you to identify more parts, yeah.
It's a question of how much dualism. So what your system is a minimally dualistic system. It's a question of like, well, why does that work?
Okay.
And the answer is the least action principle.
Okay, I like that wording.
Thanks.
That commentary.
I'm gonna grab my next
It's all right, Jen. Take a breath. Take a breath.
Is there anything left to discover after this?
Yeah, there's a lot. So once we code this, the next level is to try to code all the intersections of many of them being balanced so that we can get all the chemistry level, right? So we want to be able to use it to have a machine that will chemically do any switch between the charge and mass boundary that we're interested in.
This is why I wanted Jen here. So I'm sorry, Jen. I know you've been on a metaphysical kick recently. I understand. Can we just, at least for the moment, just focus on the physics? But the reason why I wanted Jen here is I didn't really actually click to me until more recently. But Jen has this beautiful model that she's done of the periodic table. And just, it seems to be laid out, the edges or the vertices seem to be almost orthogonal.
Mm-hmm.
And just, I found it interesting because basically the central point, Jen, why don't you kind of explain? The central point is essentially hydrogen and kind of like a joining of the elements, because, I mean, this is your model.
I mean, this is sort of initially what I sent out to get Thad's attention. And it worked, so I was pretty happy. But I hate to bring this back into metaphysics, but it's pre-physical framing. So if we don't want to use that word, it's just how we understand what is entailed by making a time or a space measurement.
The simplest method.
The ground. It's not about simple because there's like, once you understand, you'll see every level is equally simple. It's just we're the clunky.
Yeah, it's a level of resolution.
Yeah, exactly. So there's like,
okay.
It's not quite. You're saying my thing has
least
more
action.
resolution, a better resolution. It's true that my thing has, my understanding of space-time events is higher resolution because I'm using the correct coordinate system, because I'm not presupposing that you can disentangle space and time, because you can't, because they're naturally entangled. And this is a fact that is present prior to the arising of space and time. So it is still physical. It's just pre-physical. And the way, yeah. So it's not just that that's a space-time event. That's the root of space-time events. So other space-time events are resulting from this thing, the deformations of this thing, I think, in a similar way to the way that Thad's deforming his primitives. And that's why I was wondering, you had a list of the set of deformations generally that you apply to your primitives to generate these results, i.e. the, is it fundamentals of nature?
Mm-hmm. The constants of nature? Yeah.
Yeah, is one of them like really fast spinning?
Well, the fundamentals I applied to them was just the Planck boundary conditions, or let's be more specific. If one of the boundaries was the time boundary, then I'd use the Planck time. If it was length, I'd use Planck length. But if it was charge, I could use the Planck charge or the electron charge as an option. If it was mass, I could use the Planck mass. I could use the electron mass, the proton mass, or the neutron mass as option. Or if it was Planck temperature, or if it was temperature, it would be Planck temperature. So those are all your all your options of boundaries. And whenever I have any constant of nature, I would look at its dimensions and use those boundaries to see if it gets close to the actual measurement of that constant. In a lot of cases, it's already there for the first significant digit, 7 significant digits. And if it's not, it has to be multiplied by either J1 or J1 squared, which is the fine structure constant, or divided by that, or 2 pi, or times by 2 pi, or it's either pi or J1s, basically.
And you're assuming at this point these are like some type of geometric attributes of vacuum?
They're partitionings of the medium.
See, because you're saying partitioning, and the way I understand it is observations. So the trying to bridge the boundary observation gap at this point.
Okay, let's do a little. If we have a wave front on the surface of water, it's circular and it's coming out and out and out and spreading and spreading. But the amplitude of the wave is getting smaller and smaller and smaller because it's stretching and stretching and stretching, right?
Amplitude relative to what? Do you mean displacement relative to the pure form of an expanding circle?
To the observer, to the surface of the water, to that frame. So we're quantifying the energy basically of the wave, right?
Are you saying the density gets smaller? The energy density in the wavefront as it moves because it's getting bigger?
Yeah.
I'm sorry, I'm not even sure if I'm following your. I'm actually quite terrible at visualizing this stuff.
As the wave spreads and spreads and spreads,
okay.
If the medium was infinitely divisible, it would just keep spreading with an amplitude that was decreasing at a very, very smooth rate. There wouldn't be a quick drop off. But when the wave approaches the energy level of rotating the molecules themselves in the medium, then there's a much quicker drop off because it's forming a new boundary. It's taking the energy to do something new that it wasn't doing before. So before it's just spreading and spreading, taking up more and more area. And now it's spreading plus dividing among the molecules.
So absorption into a molecule is a type of boundary formation?
A rotation is a boundary formation, yeah.
And the rotation is caused by absorption?
In this case,
AKA
yes.
Going in
that case, yeah.
Basically a quantization of energy. Okay, sorry, can we just repeat that? So absorbing causes. Okay.
So we have one kind of way that the energy is dispersing as the wave's going bigger and bigger and bigger. And then at some transition scale, the energy that you're talking about is now on the same scale of the energy it takes to set to the internal medium can divide on. So when you get to that scale, you also lose energy under those actions. So you don't just smoothly lose energy. Now you lose energy faster at that scale. It seems frozen. I don't know. Are we still communicating?
Oh no, I was looking for. Oh no, I think no, her and she's up over there in Canada. She doesn't always have the best signal. I was just trying to find a little thing for there. But the reason why, just because when I was looking at her model, she kind of just started to explain that the way she had things parameterized and kind of those pyramid things. Let me bring it back up here. basically what she was doing is it was also based upon charge. And basically I kind of got to this because Professor Wolfram, he was doing a science Q&A, and somebody had talked about snowflakes. And at one point he's like, well, it's a hexagonal structure. And he's going through there. I'm like, all right, so you have some point, and then there's 6 other points around that. That's interesting. So I kind of started to delve into that. I was listening to that, and then I popped on Wolfram Alpha. And what I ended up doing is I'm like, okay, what are some of the relationships between maybe like the proton, the electron, and everything, just standard things like that. So I went in there and I started playing on Wolfram Alpha. And when we went there,
I love you say playing on Wolfram Alpha.
The crazy thing is gamer is probably one of the longest identities I've ever held. And I used to be a hardcore gamer. I lost like a year of my life to World of Warcraft. Server first, level 80 death limit. Apparently that means stuff to people nowadays. But I'm on there and I'm like, I'm treating it like a video game. It's like, it's addicting. You just start looking at what's happening. And where was it? Which parameter there? Oh, I think. Okay, that's what it was. Diameter. No, excuse me, radius. Just because that was one of the first things I also noticed as well when I started playing around. I started getting these different dimensions where it would be okay. It would be like length over time or something like charge squared. Could you kind of give us what you've learned over your quest period of that about when you're getting these different things like charge over mass squared or some of these different units? I'm like, I've never heard that before. Give folks just a quick over about what
I think maybe
learned.
the easiest thing is to try to break them down to their fundamentals. So there's a lot of units that you could be talking about in science or with measurements, right? But it's important to know there's some better units than others when we're doing fundamental physics, right? So keeping the units into the SI units are very important. And also, so when you're trying to explore the concept of nature, so let's work through the prescription really quick. You have the primary action on a primary set of boundaries times by 1 plus or minus a terminal action on the terminal boundaries. Okay, the terminal boundaries are always one thing. It's always the Planck length times by the Planck mass divided by the Planck charge squared. That's a whole interesting story on itself, but let's keep going. That one's fixed. So when you know those numbers, which you can get from our predictions here from our minimal balance, out to any digit you want. So you know that exact boundary. So that box symbol I use it because it's in all the structure.
It gives you the refinement that you, and that was the one thing I was just kind of missing because I hadn't spent the full time because I kept saying it and then I would kind of add it in, but I wasn't taking its full original derivation, which is always why once you get to that 7th digit or so, and that was one of the things. And then I heard you mention it's like, and then I noticed this. So I'm like, okay, so it wasn't just me. Good.
Yep. All right. So once we have that structure, you can just put in your number, and you put in, or you can ignore the right-hand part. You can ignore the whole terminal part, meaning put in a terminal action equal to 0. So that 1 plus or minus 0 all just goes away. Okay. And that means that the answer you're going to get now should only be right up to the first 7-ish significant digits. Okay. It could be 9, it could be 5, depends on what that coefficient or the other one could be, how many digits it has in it. All right, but still, it's going to give you a really good answer. So an answer that's good at the 7 significant digits, as far as your eye is concerned, that's better than your eye is doing. So that's a phenomenally good start. All right, so you ignore the second part, you put in the constant nature number, and for the boundaries, you just look at the dimensions in the number. Okay, so if it's got 4 different dimensions or 2 different dimensions, and if they're divided by each other or 1 squared first, that's what I'm talking about, the meters squared over kilograms are set example, okay? Whatever the dimensions of the number is, you look at those dimensions and then you turn those dimensions into the Planck versions, right? And then check to see, does that get me close to the actual right number? Because some of them have some options. If one of the boundaries is time based, it's going to be Planck time, only option. Right. If it's space based or length based, it's the Planck length, only option. If it's the Planck charge, Or if it's charge-based, if the dimension is the dimension of charge, then it could be the Planck charge boundary itself, or it could be the electron charge. You have 2 options. If it's mass, you have 4 options. You have the Planck mass boundary itself. You have its balanced geometric arrangement turns into the electron mass, or you have the way that that balance partitions, which is the proton mass, or you have the way that partitioning comes back together orthogonally, which defines the neutron's mass. So you have those 4 options. And if the dimension is the dimension of temperature, then it's the Planck temperature boundary. So those are your options. And it's not hard to find which one it has to be. You know of the lists, which arrangement they have to be from the dimensions in your constant. And you only have a few options there, and which one gets you to the right closest number, right? Then if your number is not already right for the first 7 significant digits, and you've gotten as close as you could among your options, that means that your primary action isn't 1. So then you just solve for your primary action. But here's the gold, here's the genius of it. Every time it's not 1, it's either pi, or 2 pi, or 4 pi, or 1 over pi, or 1 over 2 pi, or 1 over 4 pi, or maybe there's a 2 pi squared in there, or J1, 1 over J1, J1 squared, 1 over J1 squared, right? Those are the partition parameters that always required to make it work. If it's not 1, it's always one of those. That's a huge clue that on the first side of the thing, the only partitions allowed are either pi's or J1s. All right. On the other side, that means you got a little clue about what the other side is going to be allowing, right? But without the clues now you know where to search, and that gives you the prescription to search. And you might not get the right answers all the time. This is an interesting new way of doing something algebraically. What this does is it gives you an interfacing with asking the questions, but it gives you access to a field of false positives. Instead of being in a field where there's just no conversation, we're waiting for a genius to come up with some new idea. Now you're thrown into a field where there's maybe 6 ideas, right? And you have to pick which one's the best. So you have to start getting good. But maybe you don't trust that you already know which one's right. So you write down all 6 good ideas. That's what I did. Every time. If Wolfram Alpha has more than 1 possible answers that at least look like, well, maybe if I was an expert in that field already, I would be able to explain that one. It looks simple enough. Even if I don't recognize the constant yet, maybe that one I could explain. I write all those down and then go look up the constants, right? Well, you can do the same thing. So that's the process there.
It sounds like a lot of it's kind of flowed through each other, and it actually kind of sounds like what I've heard more recently on some of the Wolfram Physics project, where they're kind of exploring meta-mathematics there. And what they're kind of going through, and when you start almost doing proofs, and at least this is what I have in my head, it's like, all right, here are those proofs, here's how we can derive them to be true. Where have we explored within mathematics? And if you're exploring an area and you find out, well, that's incorrect, doesn't mean it wasn't valuable, because now you have that piece of information, knowing that that is the bounds. That's the bounds. It's almost as if we could come together there, we could get to the closest derivation of what is actually going on.
Yeah. Okay, so you want to be the first person I share this with, at least not in person?
Sure.
All right, another symmetry that, let's see if I can see this here. Yeah, another symmetry that we're really interested in here is the symmetry of quaternions. So the quaternion logic has this rule in it. In quaternion logic, it has to hold the AC minus BD squared plus AD plus BC squared equals A squared plus B squared times C squared plus D squared. Now, in this case, it turns out that any labeling A, B, C, D of the imaginary and real parts of J3 and 4, so of our 2 complex partition constants in our hyperbolic vortex, okay? Any labeling of its real and imaginary parts, you can pick any order you want to label it, any one of them A, any of them B, any C, and any D, and then put it in this equation, and it'll be true. Not only will it be true, which makes it super symmetrically true because we can do any labeling, it's not only true in any order, but all orderings also give you this, the radius of the hyperbolic vortex of the 4th power. So the logic of the 4th power arrangement here in this structure is also encoding the algebra of quantum mechanics, of quaternions.
Okay. Well, what equals the quaternions again? Minus the 4th power, J.
So quaternions are 4-dimensional algebra.
it's the sphere that essentially you can go to the point where basically it starts going the other way.
No, it's something more general than that. So we have the real number line, right? And we have XY plane, or you can have the complex plane where you have the real numbers and then imaginary numbers. Okay, but if you go into a 4-dimensional space where you have two complex numbers that you're putting together,
yeah.
then the rules for a self-closed operating system. So if you can still have plus and minus and divide and multiply and all the operations of math, then that 4-dimensional set of rules is called Quaternions. And that's the operation that are set by the constructive parameters of our external domain.
Is this where triple double periodicity comes in?
Yeah, yes, partially.
Just because when I see those words, I'm like, okay, 3. I'm like relatability. Ooh, 3 spatial dimensions. I'm like double. I'm like, oh, we're existing in a world of double cover, and you seem to always have just different actions, whether it's electric, and magnetic, and periodicity. Well, that sounds like a circle, some form of rotation there. I'm like,
and if it's triple doubly periodic, what does doubly periodic mean?
I'm going with a double cover, and as far as I understand, and again, I haven't been able to find any really good images, and again, just lack on my part of like the Geisking manifold there. But I'm looking at the hyperbolic figure 8 knots complement. I'm looking at what's going on there, trying to intuit in my head what you've taught me. In that, I'm like, okay, these are separated planes. If you had blue in here, if you had red in here, there will be some form of flow. And my thought is, I want to model that flow. I want to see what's going on, because according to one of Professor Segerman's videos, he's like, this knot complement, it also generates rotation. And I find that fascinating.
Yeah. So we have the inside shape you're visualizing pretty well. Now, what we're going to do is we're going to imagine, well, we have to unwind the inside to define the shape of the internal boundary of the outside. Let's make sure if that sentence was clear before I move on. Okay, so the inside is mirror image partitioning compared to the outside. Okay, but the shape of the outside is, well, before I get to shape, the outside is what we call a projective space, meaning it's basically being balanced on the internal actions. So it's being projected from the inside, okay? So it has a fixed limited bound, and that's the easiest part to understand is the sphere. But then at some point we get to a boundary where the projection is coming from, right? It's no, if you cross that boundary, it's no longer just coming from you. Now something else is also included in the picture, so it gets more complicated. All right, so, but in this picture, there's not just a scale cut off, a new spherical size in which if you cross that boundary, the projection is now different. No, it's that you reach one scale, and from that scale to the other smaller scale inside, there's interesting things happening. That's the interesting boundary, how it twists and folds and wraps itself. So the geometry of how things are getting broken up from the big one to the small one of the internal bounds of the projective external world are what we're trying to now get a real good picture for, right? That's the things we need to really focus on. But notice that leaves us only missing sharp image on the details between the Planck mass and Planck charge boundaries now in your head, right? You should have a very clear picture for the inside of the hyperbolic figure 8 knot. And the outside is just a sphere. Then you zoom way in on the sphere, and then it gets to, okay, now I don't know exactly how these two boundaries fit together, but I know out there they look like a sphere. So that's where you're at, and that's what I provided. But I'm trying now to get it in the computer so I can show you every single possible intersection that's happening.
So an electron, a black hole, and the universe walk into a bar. I say that jokingly. Is there any relevance
between electrons, black holes, and universes?
Does it depend upon the observer?
No, I would say that. So what we're modeling here is in this minimal arena. It has all of the minimal partition parameters that we now label in quantum field theory. Meaning, if you label the smallest partitioning time and that field of balance that's resting on it ultimately is all in the field of time. But you zoom out, and then you have a different action, a different size you can reach, in which there's a new boundary being formed, a new balance, and there's new resonation where everything on that scale is now under balance. So that's under the balance of space. I forget where we started, so I need to remember where I'm going. Remind me, what was the beginning of this?
We were basically going into the new stuff. We were talking about Quaternions a bit before, or we talk about after that.
Just right before I started the last time talking.
Hold on, somebody. Oh no, the charge. What's going on with the actual right around the charge? Because it's like, okay, we have the sphere, we got a knotted center. What's going on at that midpoint?
So we have a vortex, and now we want to get the picture of the vortex clear in your head. I know you have a general idea of what a vortex is, but think you're in a domain. We'll think of it like a fluid, but as you approach, as you get smaller and smaller and smaller in this fluid, there's going to be a domain now where you're being partitioned, meaning divided across in more than one way. You could do in one thing, but now you're doing more than one thing. That's being a divider. So you're inventing a new boundary under this partitioning. All right, but there's going to be a limit to the partitioning. So the partitioning can continue as you go internally, but you're going to reach another limit at some point, a smaller scale, where there's another kind of partitioning happening. And those two partitionings have to fit inside of each other, not against, well, I mean, the language is a bit tricky until we have the exact picture, and I know you're seeing what I'm seeing here. You could say against each other, inside of each other. There's no gap, is what I mean, okay? But the gap, it could be that you can have a circle inside of another circle. It doesn't need to be a circle that's rolling along the edge on the outside. It could be a circle that's rolling along the edges on the inside, if that makes some sort of sense.
Now, I'm not sure I exactly follow, but just what kind of comes to my mind is I don't know, for some reason just kind of starts popping up there, and then I look at some of those diagrams, some of those generated things, and I'm like, okay, well, I could deform either of those into a circle. They have a circle within each circle there, and then I start getting metaphysical, and I'm like, wow, humanity's pretty freaking awesome.
It is awesome. I mean, all of it's awesome just to keep you investigating. But most importantly, to remember that simply by figuring things out, I mean, there's a lot left to figure out, but the reward of figuring them out goes beyond anything we're lost in the modern drama on, right? All of it. I mean, think when we're in the Star Trek age where we literally have replicators, where you have the intimate knowledge of how to make something, a machine that can transform anything that right now is around you as free or considered garbage into anything that you know exists. Now it's really a game of just knowing what exists. You have the options limited only by what you can imagine, because you can create anything. Resources aren't the thing that will hold you back. Resources aren't the thing we aggregate around, the thing that we look for. We don't pay attention to money because resources aren't a thing anymore like that, right? That's
it's well, we have the ability to actually enter like a true post-scarcity environment. If we actually have the ability to manipulate different things, we were discussing a little bit before the show, I'm seeing multi-layered twisted graphene apparently having superconductive properties at much higher temperatures. I'm like, okay, now if we actually have
all of our investigations so far, and I used to also work on graphene, so I really like that one, but they're all handicapped by this vagary that we currently have in our model of, say, quantum mechanics or quantum field theory. There isn't a picture that's being attached where you can then go become an expert and stare and play with the mechanics or the gears in the clock and then develop an intuition about, well, why don't we do this? Or how about I build it this way instead? There's not a picture for you to tinker with. So we've been just playing with the statistical blow things up more and try to make stuff happen. This is a complete revolution where we don't have to waste energy to make something happen. We have to understand something better to make it happen.
Have we spent too much time just shutting up and calculating, in your opinion?
Yes, but honestly, in my opinion, I'm probably a little more outspoken on a further end on that topic.
Okay, no, I'm sorry.
Well, I feel like we've almost, if not completely, lost academia in this world. I think we should more appropriately call it business-damia right now, because in academia, it should be filled full of individuals who feel like they're being empowered to ask the biggest questions they can and honestly seek them to gain the most knowledge they can for the rest of humanity during their career. Not, oh, after you retire, then maybe it's okay to work on that. No, that's how it used to be in academia. You used to prize people because of their interest and their passion to chase something, not, well, what do the business people want you to work on? That's just ridiculous. If we're only allowed to focus on what the people who have already proven themselves to only focus on the worst things, they can't be the leaders.
I think a part of this is probably just a current component of the system, because as somebody that did go to school for business, I apologize. This is basically what they teach you. It's like, what do you want to do? Minimize risk.
The only focus, because it becomes so irrelevant when we get to the next stage, right? All this stuff about trying to claim how much stuff you have in property and prestige, it's all around the control of items of basically power and stuff. That doesn't need to be what humans are anymore. I think we're all ready to move on to the next stage. We're all ready for real relationships. We're all ready for actual deep conversations where we can come to them knowing, hey, I don't know this thing and I really want to know it. Doesn't mean the other person has the answer, but right now I feel like we're in a world where we shun people from being ignorant. And the thing is, we're all ignorant. We're all deeply and profoundly ignorant. We don't even know what the rules of reality are yet. We're still at a stage where we're in a level of ignorance that we can point to. It's not that we don't even know we're ignorant of. We have a whole pile of things we know we're ignorant of. So that's both entertaining but also exciting, right? It means you're never going to end in a situation where you don't have something powerful to do.
Well, that's the thing. And so I feel like as a longtime gamer, I feel like this is one of those special high-end strategy guides to a lot of my favorite games, just because I'm looking at this, and initially I'm so glad you just kind of just eloquently just wove that together, because one of my main things is, after I had initially interviewed you, I'm like, okay, I have some ideas. Do I really know what's going on? Have I spent the time yet? Have I investigated these other things? No, I actually got a little bit depressed there, because I'm like, well, if that solved it, that game over, man. We're done. And then I'm sitting there and I actually think I'd explore more. I'm like, no, this is just the beginning. We're actually just learning how to play the game.
The biggest news here isn't that this is necessarily right. I'm never going to claim that a model is right. That's pointless. The biggest news is, one, this gave us a new way to investigate. Literally, you and I, without feeling like an expert in math even, right, with the tool of Wolfram Alpha and with this simple prescription, can personally investigate all the constants in nature. That's something that couldn't be done before. That's something that any nerd like me before would have given their life for the chance to do before, right? We're living in an amazing era now, and that psychotechnology, which is trivial algebraically, just needed to know those boundaries were there, right? But with that knowledge, you can now investigate things and start developing your own intuition. That's what's most valuable in all of this. I mean, nobody wants to just have an answer. You want to have the intuition of the answer. You want to own it yourself. You don't want to just know that some smart person somewhere else has finally figured it out.
we're given the opportunity for the people to play the game.
Yeah.
And just all I know is I'm starting to hear these things about, oh, there's NFTs. Oh, this person has this very special picture icon and they're spending thousands of dollars on it. I'm like, that's worth thousands of dollars. What happens if people are actually putting in the time, putting in the work?
Mm-hmm.
I don't know, maybe solving proofs, and you come up with a cool little achievement or something, kind of like we had in World of Warcraft. It's like, this was the person that solved this. They can hold on to this if it's worth something. I mean, I'm talking about kind of more of a transitionary period where it's like, you don't necessarily need this. I'm like, okay, how will we have more development and intake of this? Well, you need the proper incentive structure as well.
Mm-hmm.
So it's like, okay, let's get people to start doing useful things rather than, I don't know, oh, look, some person that's famous did something that
Yeah.
was kind of silly. This person, and just make this content just kind of hating on people just because that's what's heavily monetizable now. That's what makes me sad. I want
Yeah,
people
it's true.
to be rewarded for doing great quality work. I'm just like, that's how we can continue to have
Yeah.
exponential gains. And
That might
like
be
you
one of the
said,
things I'm most excited about is when I'm not claiming I believe this revolution is going to happen during my lifetime, I hope, but I believe it also can if we all get our act together. But when it does happen for humanity, that we have the resource thing taken care of, that every human's born into a world where they never have to pay for something, because that's not how you get things. You just need to know what you need. Just like now, if you know how to ask on Google, you can get some information. If you know what you want, you can get it. You just need to know what you want in the future. But when we get there, our mode of operation is going to be completely different. It might take a generation to adopt, or more than one, but we're going to live in a world in which it's not about prestige. It's about what can you reach before you perish. Even if we end up living longer, still, what can you reach? And whatever you do reach, you put out the most beautiful version of it before you die, because that gets to live for everyone from now on, right? It's a search for how much the most beautiful you can contribute to humanity before you go, instead of how much attention can you get from the masses, which means by default, it's got to be negative.
Well, there's old saying in news, when fortunately, if it bleeds, it leads. And that's more or less perfectly translated onto the internet, like you were talking about there.
Mhm.
But just in my mind, like you were saying, if we can clear the cachet of hatred from our heads and hearts, it's like we can figure this stuff out. And in my mind, I have maybe in a millennia, if we can just get over ourselves, they'll have internet archaeologists going back, sifting through, like we have with like ancient Greek cities and just all over the world, being like, what was actually going on? Who are the folks that had put out these ideas? What were the interactions? And now we just have additional higher dimensionality, rather than like, here's some pottery and here was a mother with her child. And we're making all these assumptions. Now we can actually know what's going on to a much higher precision of what happened in the past, if we can continue to refine that and actually get folks interested in charting different things out. Sky's the limit and space is the place.
Yep. Space is the place. We can still get there.
But that we've been going on an hour and a half now. Were there any other things you kind of wanted to delve in specifically?
No, I mean, I'm starting up this think tank real soon, officially next week. So I think we'll be going into a lot of things specifically soon. So
cool.
Yeah, this is great catching up with you. And I don't know, when I get the next book out next month, it'll probably be like March 17th. That's my target at this point. Then I'll send you a version, and you can tell me how much more you understand, what new questions you actually have. Most importantly, what is the next pressing thing that isn't clear, right? I want to know how much of the story is absorbed, but also what question does it inspire in you, so that I can, if it's not already on my list of questions too, that I'll either answer it or chase it.
Any book where the final chapters are asking very specific questions, some of them have answers, maybe some of them do not, gives me a lot of hope. But cool. Yeah, that's all I really got for now. Thad, thank you so much for joining us again. Again, we have 44, Thad's most recent book, soon to be updated, hopefully next month. And just keep us in the loop of what's going on, and just keep the good work up. Good luck with the think tank and everything. And on that, be said, everybody.
Peace.
Be safe. And again, we have not yet proven
it's turtles all the way down.
That's all we got for now, folks. Take care of yourselves, everyone. Where's the thing? Oh, there's the thing. No, the wrong thing. Okay, we'll just end it.